let's finish. There's just a little bit from last time that we didn't quite finish. Let's talk about, or before we do that, let's do, if we have sodium. What in the world? That's weird. What is the charge of the sodium ion? Use your periodic table. Sodium is number 11 on the periodic table. What is the charge of the sodium ion? What? Positive 1. So the symbol we would write Na1 plus or Na plus. Good? What about nitrogen?
Plus or minus 3?
Minus 3, so it'd be N3 minus. That's how we write it. Do we all understand? Raise your hand if you need a review. Okay. How did you know it was minus 3?
Because of the thing at the top of that we wrote. This
Okay. So here we go. Okay, on our periodic table, we have the number of valence electrons as the group number. And remember, in this section, it's just the second number in the group number. Y'all with me? Oops.
Is the number at the top of the square in the periodic table the amount of protons in it?
This one right here?
Yeah.
Yeah, that's the atomic number.
Okay.
Okay. But for the valence electrons, these are the electrons that participate in a chemical reaction, right? So this group will have 1 valence electron. This group will have 2. This group will have 3, 4, 5, 6, 7, and 8, except for that one right there has 2. And we'll talk about why that is today. Remember this? No? Okay, good. So if fluorine has 7 valence electrons, if we draw this, whoops. So fluorine has 2 electrons on the first energy level. We'll talk about how we know. And it has 7. 1, 2, 3, 4, 5, 6, 7. It has 7 electrons on the outside energy level. But how many does it want to have? 8, just like the noble gases, right? It wants to have a full outside layer. You with me? And so it's going to gain 1 more. It has 9 electrons total. It's going to gain 1 to be like neon. Well, it's gaining a negative because the electrons are negative. That's why fluorine is going to be F1 minus, or just F minus. Are we good? What about helium? What is the charge of a helium ion?
0.
Yeah, it will not be an ion. It's a noble gas. It doesn't want to gain or lose electrons. You with me? So this one will not become an ion. Questions so far? Okay. Last thing we got to cover, so that was just a little review. Last thing, so we've been talking about electrons. Those are on the outside. What about what's on the inside? Nuclear change. So we have 2 types of nuclear decay. We're only going to talk about those 2 types, and that's it. And we're going to just keep it simple here. So here we go. We have alpha decay. an alpha particle is a helium nucleus. That means it's just the nucleus of helium, doesn't have any electrons. How many protons does helium have? Look at your periodic table. 2, because helium has atomic number 2. Good? How many neutrons does most heliums have? 2. So the symbol we use for an alpha particle is 4,2He. Do you understand that symbol, what that means? This is the isotope symbol we learned last time. This is the mass number, means protons plus neutrons, right? And this is the atomic number, or the number of protons. Are we good? Okay? This is an alpha particle. Do you remember when we talked about Ernest Rutherford doing his gold foil experiment? He used alpha particles. That's what these were. Okay? And alpha decay, what does decay mean? Yeah, breaking down, right? Getting less, right? So, for example, if we have uranium-238, will undergo alpha decay. And you don't have to memorize this, okay? But you do have to know what is the product of alpha decay from uranium. So we're writing a chemical equation here. In a chemical equation, we have the products on the left side. Sorry. I don't know why I said that. The reactants on the left side and the products on the right side. Does that make sense in your mind why we do that? These guys react to form the products. Yeah, this is a chemical equation. Okay, are we good? Okay. And what we produce, so if alpha decays off of this nucleus, so if we have, here's the uranium nucleus, and we have the electrons buzzing around it, right? I'm not going to draw those. Then what happens is uranium decays off of this. So we're left with alpha particle plus some other thing. This is 2 protons less and 2 neutrons less, because it just got rid of an alpha particle. Are you with me? So what is left? It has a mass of 238 to start with. What mass did it get rid of? 4. So how much mass does it have now? 234. Are you all with me? Talk to me, people. When you're silent, that scares me. Do we get this?
I'm just writing it down real quick.
We started with 238. We got rid of 4. That leaves us with 234. Questions? Yeah.
90 protons?
We have we have 92 protons to begin with. We lose 2, so we're left with 90 protons. What element has 90 protons? Look at your periodic table. Thorium. This is my answer, and this is what I'll be asking you on a test. What is the product, or what will remain after uranium undergoes alpha decay? But you have to know uranium is this right here. Question.
So is helium
Yep, this is the alpha particle.
Thorium, the mass number is 232.
What?
For thorium, the mass number is 232.
Oh, that's the atomic mass. Remember, the mass number is how many protons and neutrons it has. What's the atomic mass? The weighted average of all the isotopes of that element, right? So for this particular atom, the mass is 234. You with me? Good comment. Yeah.
I understand where you get the 92 for uranium.
Uh-huh.
How are you getting the neutrons?
All right, so this is not number of neutrons. This is the there's none of those numbers is the number of neutrons. So to find number of neutrons, we subtract the number of protons from the mass number. Right?
And the top number is neutrons plus protons.
That's right.
So it just is.
238 minus 92, and that's the number of protons, or neutrons, sorry. Are we good? Does that make sense in everybody's mind? If it doesn't, I can show you another way. Who wants another way? Okay, here we go. I have 238 equals, I'm going to represent that arrow as an equal sign, equals 4 plus x. I don't know what it is. And then I can do 92 equals 2 plus y. And I'm looking for x, y, z. This is what I'm looking for. You following? Now we can just do a little bit of algebra. We subtract 4 to both sides, and we got x is equal to 238. Sorry, 234. You with me? We do the same thing with this one. Subtract 2 to both sides, and we got y is equal to 90. So we have 234, 90, and then we look on the periodic table. Whatever has an atomic number of 90 is thorium. Anybody like that way better? Then don't do it that way. If you don't like it, don't do it that way. I don't like it either. It takes too much time.
So do we have the periodic table with us?
What?
In the test, do we have that periodic table?
Yes. Well, on the unit test, you have whatever you want. So make sure you, before you start that test, you have 120 minutes to take the test. Before you start it, make sure you're all ready.
So the unit test is the one that's open book, and it's the midterm and the end, or the final, that's the one where you need that double-sided.
That's right. So if I were you, though, I would be getting that paper ready and using it, right? That way you're familiar with everything that's on there, and you can adjust. You can take stuff off, put more stuff on it, right?
Is there a time limit in the test for the unit test?
Yes, 120 minutes.
Okay.
So listen, everybody. The test is scheduled to be done on June 2nd, yeah? I hope we get through all of this stuff. If we don't just take the test, guys. Okay? That due date's not set in stone. But don't wait 3 months later, okay? If you don't take it after a week, I'll probably just put a 0 in place of it. So anyway, let's see how far we can get today. Make sense? So don't rush to get that test done because it says June 2nd. Any questions on alpha decay? Why does it do this? Because it's unstable. Okay? It's unstable, so the nucleus is just going to change. And you can't slow it down and you can't speed it up. It'll just happen. It's happening today as we speak. In the earth, there's material that is radioactive. Okay? It just happens. Can't speed it up, can't slow it down, as we know. Yeah.
So the alpha decay
What's that?
Do we have to do it always in the equilibrium? Like the
If it's alpha decay, alpha particle is always this, yes.
that always subtract from the atomic mass and always subtract
That's right.
from the proton mass.
Uh-huh. Are we good? Ready to move on to beta decay? Okay, here we go. Beta decay. So first of all, a beta particle is an electron. 0, -1, E. This is the symbol that we use for a beta particle. Know that. So when we use beta decay, we're going to use this symbol. When we use alpha decay, we use this symbol. Good? So get those down. And here's an example of beta decay. We have carbon 14. What's the atomic number for carbon? Look at your periodic table. 6. And we decay a beta particle, so 0, -1, E. What are we left with? Can you do this without me helping you? Try it. It's the same way. So look at the periodic table to determine what element it is. Do you have a periodic table? Right up there.
Nitrogen,
What is it?
nitrogen,
Nitrogen 14. Everybody get that? Now let's see. Watch, guys. Anytime you get an answer, check it. Let's check this one over here. Is 90 plus 2 equal to 92? Is 234 plus 4 equal to 238? That's how we know we did it right. Come over here. 7 plus a -1. What's 7 plus a -1, guys? 6. 14 plus 0 is 14. A lot of people make mistakes on this one, on the test and on the midterm, because they call this what? 5? Anybody put 5? That's a common mistake people make. This is a negative number. So we have to add. That's why I show you the algebraic way. So if we do the algebraic way on this one, it's 14 equals 0 plus what number? And that's going to give us x equals 14, right? And then we do 6 equals -1 plus what number? So we add 1 because it says -1, so we do the inverse operation, right? To both sides. And that gives us y is equal to 7.
Because it's an electron.
That's right. Are you with me? Yeah.
How do we know when we're plus and when we're minus?
How do you know when you plus or when you minus?
Yeah.
Good question. 3x plus 2 equals 5. Are we going to add or subtract?
No, I mean like up. If you go up, it's like in that one like plus minus.
Uh-huh.
When do we know when it's plus, when it's minus?
Well, a beta particle is always has a negative charge.
Yeah.
Alpha particle has a positive charge.
Yeah.
So, are you wondering how you know I subtracted 2 here?
No. It's just you put plus and minus, so I was like, sometimes you can do plus and sometimes you can do minus. That's what I was wondering.
Or was it just an underlined plus? Right.
Right here?
Yeah, the red.
Right there?
Yeah.
Okay, yeah, I just underlined it.
Oh, okay, sorry.
Sorry, no.
Did you remember to start the recording?
Yes, I did, thank you. Did that make sense?
Yeah, I was.
Yeah, sorry about that. Yeah, it's not plus or minus. Yeah, it's always plus. Always. That when we have an equation, we have some. So for example, we have H2 plus O2 gives us H2O. It's always going to be plus. I just wrote minus again. It's always going to be positive. What?
It should be 2H2O.
It's not balanced yet, but yes. We'll get there. We're not there yet. Good? Did I answer everybody's question? Should we try another one? Okay. Okay, if we have, I'm going to give you two of them, and I'm going to have you do them by yourself. If we have, let's say, gold 198, and it undergoes alpha decay, I want to know the product. What will be left over after gold 198 undergoes alpha decay? And then, if I have hydrogen 3, what will be left if it undergoes beta decay? So this is alpha decay. And this is beta decay. That's how it will be given to you on the test. I'm not going to tell you what the alpha particle is. I'm not going to tell you what the beta particle is. You just have to know. Not always. That's the atomic mass. That's the mass number. I will give you the mass number.
Okay.
Do you get the difference? The atomic mass is the weighted average of all of the isotopes. Okay? Okay, any questions on this? Did I make a mistake? Are we good? Yeah, question. We good? Okay. Ready to move on? All right. Today we are going to talk about the periodic table. If you understand how to read the periodic table, well, that'll be for your benefit because you get to use the periodic table on every test, right? So let's make sure we understand how to read this. So I'm not gonna give you all of the history about the periodic table. Is that okay? Because we're already time limited, and it's not on the test anyway. Are we good? All right. So why do we call the periodic table the periodic table? Any ideas? No, just tell us? Okay. Well, we have periods. Periods 1. So I'll do periods in red. 1, 2, 3, 4, 5, 6, 7. So these guys are the periods. What does periodic mean? What's a period? What's the Earth's period around the sun?
A year?
A year. What's the Earth's period around its own axis?
A day?
A day. Are you with me? Okay, and there's other ways periods are used as well. It's a time period usually. Okay? But on the periodic table, it's not time. But something repeats. So what happens? The Earth goes around the sun, and then what happens? It does it again. And then what happens? It keeps doing it, right? It's periodic. Okay? So here in green, I'm going to put groups. We have group 1, 2, 3, 4, and they're all labeled all the way to 18. You with me? So these right here are the groups. So in group 1, they have similar properties. In group 2, those elements have similar properties that are different than group 1. Why is that? Any ideas? We talked about it last time. What's the same with all of these elements in group 1? They have one valence they'll be positive 1, but before they become ions, they have one valence electron. And in group 2, they have 2 valence electrons. And in group 17, they have 7 valence electrons. What part of the atom determines the properties of an element? There's 3 parts of the atom. What part of the atom determines the properties of an element? Not quite.
Is it the protons?
I'll give you a hint. Can I touch this?
Yes. The electrons.
What part of this bottle am I touching? The outside. The only part that interacts with anything is the outside of the atom. What is on the outside of the atom? Electrons. Well, everything, all these elements in group 1 have 1 valence electron. 1 electron on the outside. Everything in group 2 have 2 electrons on the outside. Everything in group 17 have 7 electrons on the outside. Are you with me? Okay? So, what happens is, in period 1, we have hydrogen, then helium. They're different, right? They have different properties. Then, what's after number 2? Lithium. Has similar properties to hydrogen, kind of. Hydrogen's a weirdo, so we won't go there. But then you got beryllium, and then you go down to here, and then you have sodium. Well, sodium has similar properties to lithium. Let's talk about them. So lithium, you guys ever heard of lithium? Where have you heard lithium? Yeah. Batteries. Lithium-ion batteries, like on our cell phones, right? Like in your maybe a drill, right? A charging battery, right? Lithium batteries. Why do we use lithium batteries? Have you guys ever gone to the store and bought AAA batteries, AA batteries? And there's one pack that costs $3 for a pack of 4. And another pack right next to it costs $16. Like, whoa, I'm not gonna get it. You guys ever do that? Did you ever see that? Why do they cost $16? Because they're lithium. They're better. They last longer. And what's the property that makes them last longer? They're more reactive. We'll talk about this in a minute, but they're more reactive. But what about sodium?
Less reactive.
they're highly reactive. I have some right here. Should we put this in some water and see what happens? You saying no? Oh, you want to? Okay. So if we have time, we'll do that, okay? So they're highly reactive. And potassium is even more reactive. Rubidium, even more reactive. You throw it in water, I'm not going to tell you what's going to happen, but we'll see. Okay? So what repeats itself as we go through each period?
Reactivity?
The properties repeat. So these guys all have the same properties. Not the same properties, but similar properties. And then group 2, they all have similar properties. These guys all have similar properties and so on. Well, let's talk about another one. Copper, silver, and gold.
Oh, they're
What-
the coinage metals.
Oh yeah, why do we make coins out of them? Because they're shiny, right? They're pretty shiny. Well, a lot of metals are shiny, but they're also good conductors.
And
We
they
use
don't-
copper. We use copper in the walls in our electricity. Why don't we use silver? It's expensive. Why don't we use gold? Even more conductive. It's expensive, right? So in the 60s, they used to use aluminum, which is over here. It's not in the same group. That means it's not as conductive. Why do we use it? Because it's cheaper. But what happened in the 60s? A lot of houses caught on fire because too resistant to the electricity, and it caused it to heat up and burn up the houses. So, are we good?
Is that why when you put aluminum foil on both ends of a battery, it'll make a fire in the middle?
Yes. Yep. All right. Are we good with why we call it the periodic table? All right. So there are 3 classes of elements. I'm going to move on. So if you guys want to write this on one of, I put several periodic tables over there so you can have more than one. I'm going to pull out another periodic table because I'm marking the heck out of these. All right, the first one, so there's 3 classes of elements. You got to know these classes. On the test, I'll ask you what classes is this type of element, and you got to tell me.
I have a quick question.
Quest away.
So on our periodic table, it has lanthanum and acetinium. Both of those are absent on yours.
These
Does that
go
matter?
right here.
Oh,
Some periodic tables put them down here because we call these the lactinide series, and these the actinide series. But in our case in this class, we're going to keep them where they go. 57 and this is 57 and this is 89. Okay? So, in fact, what do I give you the right one? Yeah, so the periodic table I give you is correct. All right. So the first type of element is the first type of elements that we learned as human beings. What's the best type of element we know of?
Hydrogen.
We didn't even know about that. What?
Iron.
Iron. And what type of element is iron? Metal. Yeah. So here I'm going to outline the metals. So these are all metals. You can use colors, you can shade them in, you can mark them somehow on your periodic table. These are the metals. So if you want to just outline the next group that I'm going to do, the next class, this might separate the metals from the nonmetals. Or they do, actually. These guys are called the metalloids. We call it the metalloid staircase because it looks like a staircase. Can y'all see that color okay? Can you see it well enough to take notes?
Where's
Okay.
LV?
We don't have a lot, some of them.
Yeah, you won't have some of them. That's okay. These right here are relatively new. And I want to show you something real quick. You see how it has a bracket right there? Or even over here it has brackets? That means it's very, very, very unstable. The nucleus is unstable. So they don't appear in nature in general. So we won't deal with them in this class anyway. Good? Okay, we good with the metals and the metalloids? Am I going too fast? Do I need to give you time to write these down? Yes, I'm going too fast? Okay. So if you have highlighters, that's a good idea. Or you can just shade them different, right? So we can just shade all these guys. Right. Those guys are our metals, and we can put a little in there. Maybe put circles on the next one. I don't know, whatever. Whatever helps you, right? And the last type are the rest of them. These are nonmetals. Don't forget hydrogen over here. These are nonmetals.
So probably on the test, you'll give us the element and you'll ask, is this a metal or non-metal?
Yeah, I'll say, which of the following elements is considered a metalloid? Which one is considered a nonmetal? Which one is considered a metal? Yeah, that's a possible question. So if you know where this staircase is, the staircase, everything to the left is a metal, everything to the right is a nonmetal, except for hydrogen. You just have to know that one, right? Are we good? Can we move on? Okay. Let's talk about the properties of each. So we got metals, metalloids, and nonmetals. Okay. What are properties of metals that we know of?
Highly reactive.
Not all metals are. Some metals are. But
They are solid.
they are solids at room temperature, good. There is one that's not,
Like helium.
and that's mercury. So they're solid at room temperature. They are conductive. You guys know what that means? They allow electricity or heat to flow through them easily. This is why when you hold the leg of your table and put your other hand on the top of the table, which one's colder?
The metal.
Incorrect. Try it. Put one hand on the leg of the table, one hand on the top of the table. Which one is colder?
The leg.
They're the same. Yes. They have the same temperature, and guess what the temperature is? Room temperature, or the temperature of this room, 70.5 degrees. Why does the leg feel colder? Because it's a good conductor. It's conducting heat. It's taking heat from your hand more than the tabletop does. So it feels colder. You with me? That's what conductivity is. So they're also ductile.
And they have electricity can go through.
Yes, that's the same thing. Electricity or heat. We call that conductivity. Yes. So energy in general. Energy can flow easily through them. That ductile means you can make wire out of it. We can easily make wire out of metal. In fact, that's what we make wire out of, right? It's also malleable, meaning we can shape it to whatever we want. We hit it with a hammer, it'll just change shape.
Sometimes you gotta heat it up first, but yeah.
Most of the time. Okay. Are we good with that? Non-metals are brittle. What does that mean? You hit it with a hammer, what happens? It breaks. It doesn't change shape. It's not ductile. It's not malleable. It's also insulative. What does that mean? The opposite of conductive, right? So rubber, plastic, wood, these are all non-metals. They don't allow energy to transfer through them. Good? These can be solid, liquid, or gases at room temperature, so that's not going to help you. But if it's a gas, it is non-metal. Okay? So we'll just say gases are non-metal. And the metalloids, I'm going to just keep it simple. Somewhere in between. So instead of being conductive or insulative, we say semiconductive, right? Somewhere in the middle. And it makes sense because where are they located on the periodic table relative to metals and nonmetals? In the middle. Good? All right. I'm going to try to go a little fast today, so tell me if I'm going too fast, okay? So I'm going to pull out another periodic table. And I'm going to talk about the diatomic molecules here. What does the prefix di mean? Do you guys know? It means two. Di means two. Atom, two atoms of the same element. That's what diatomic molecules are. Two atoms of the same element. Now, there's 7 diatomic molecules. have to know these 7. And there's one on the test. I'm not going to tell you which one is on the test, but one of these 7.
2 atoms of the same element?
2 atoms of the same element. So what these are elements that cannot be by themselves. You can't just have one single element or atom floating around. Has to be paired up with one other of the same atom, right? It starts with number 7. So there's 7 diatomic molecules. It starts on number 7, and we draw a 7. Do you see my 7 up there? So over 3, down 4. So the first one starts on number 7. We draw a 7. How many is that? That's only 6. Our 7th one is the king of exceptions,
Helium.
hydrogen. So that means we have H2, N2, O2, F2, Cl2, Br2, and I2. These are our 7 diatomic molecules. And in nature, that's how they appear. You'll never see oxygen as O, as one atom. We're going to use that more at a later time, but you just need to know those. But there is one question on that on the exam. Any questions on diatomic molecules? All right, moving on. Sorry, I hate going this fast, but I've got to. 1 second, you want me to go back?
Yeah,
Or-
just so I can get the last one.
Hydrogen,
No,
Oh.
iodine. Never mind.
I2, yep. So the 2 goes, it's a subscript. So it's I with lowercase, the 2 goes down, right?
Okay.
All right. Next, let's talk about the groups. And so this stuff is just fact stuff. Why do we call them this? 'Cause that's what their mother called it, right? There's no, why is it supposed to be that? It's just the way it is, okay? Just got to memorize this stuff. And I don't like to have you memorize stuff, but some things you got to, okay? All right, so let's, the first group are called alkali metals. And that's this group right here. Hydrogen is not an alkali metal. It's not even a metal, right? So these are called alkali metals. And what do you need to know about these metals? I've talked about it a little bit. These are the most reactive of all metals. Most reactive metals. Good? Okay. The next group, group 2, these guys are alkaline earth metals. Not alkali, but alkaline. You guys know what the cheap batteries are called? alkaline batteries. They're reactive, but not as reactive. Good? Okay, this group right here with oxygen in it. This is not a common name, so don't spend a ton of time getting this one down, but okay. I think you'll see it somewhere. And a lot of my students say, what is that? And that's why I'm telling you. These are called chalcogens. Chalcogens. And group 17. These are called halogens. And what you need to know about these? Am I going too fast? What you need to know about these are the most reactive nonmetals. And why? Why are these the most reactive nonmetals and alkali are the most reactive metals? Can anybody think of why? Yeah. That's right. That's right. You remember the octet rule from last time? They're just one away. So these alkali metals, they just need to get rid of that one electron to be stable or to be balanced, right? And the halogens need to take one to be balanced or to be stable. When I say stable, I'm not talking about nuclear stability, but good. And the last group we need to know, noble gases. We talked about these last time. What do you need to know about the noble gases? They are the least reactive elements. Why are they the least reactive? They have a full shell, yeah. They have a full valence electron shell. Good. Does that make sense to everybody?
what is the number, I know it goes 2, 8, is the next one 16 for the shells?
Oh, you mean like for the rings, like for Bohr's model? We'll talk about that in a second. How's that? You don't need to memorize that so much. I'll show you how to use the periodic table to tell that, okay? Okay. Any questions so far? Okay, so on this worksheet, those are sample test questions. So let's take a look at this real quick. So it says classify them as metals, nonmetals, and metalloids. I'm going to leave that on you. You don't have to do it right now. But what I really want you to do is part B. From the above list of elements, group together those elements that have similar properties. So we have silver, Ag. What other element has similar properties to silver? This is a test question, ladies and gentlemen. I will ask you this type of question on the test. What other element in this list has similar properties to silver? Why copper? It's in the same column or same group. Good?
What number was the question that you asked so I can start?
This is the very first one, number 1, part B.
Oh, okay.
So what element has similar properties to chlorine in this group?
Lithium, sodium.
Iodine. Chlorine is in group 17, so any other element in group 17 has similar properties. That's why we call them halogens, right? Does that make sense? If they're in the same column or same group, they have similar properties. I want to do one more group that I forgot to mention. And I got to find another color. This group right here, these are called the transition metals. Oh, you can't read that, can you? The transition metals transition from this set of main group elements to this set of main group elements. Okay? We can only tell the number of valence electrons in the main group elements, yeah? We can only know the charge of the atom in the main group elements. So we'll talk about transition metals later. What do we call these guys down here? Where are they located? Right there. If you look at the numbers, here's 57 and here's 89. This is 72, this is 104. These get pushed inside. So what do we call these? Inner transition metals. And we'll talk about those guys later. But those are the different groups. Okay? Did I go too fast? Kind of. So here's what I've had students do in the past. Do you get this on the midterm or the final? The paper that you're drawing, all these colors and stuff on? No. But I've had students take a picture of it, shrink it down, copy it, and put it on, right? Whatever you want to do, you can do that. I mean, on the unit test, you can use this because it's your notes, right? So you can have this stuff if you need it. Are we good? Or if you're technical savvy, just put all this stuff, scan it in, put it on a Google, just a Google sheet or whatever, and put everything on there that you need and print it out, right? Whatever. Yeah.
Does it absolutely have to be printed?
If you want to use it, yes.
Okay.
Yep. Because on the midterm and the final, we're taking it in class or in the testing center.
Am I able to take it in those spots?
Yeah, you can come in here. Yeah.
May be able to shrink it, but can I see it?
Oh, yeah.
We need a good enough.
Got it. But you have two sides, right? You have two sides on that paper.
Oh, magnifying.
So if you don't think you can put it on there, store it up here. Whatever you got to do.
Or bring a microscope.
Or big a magnifying glass, right? Microscope might be too much, but okay. Are we good about the different groups and classes? All right. Let's move on. I think we're doing good as far as time goes. So that's the periodic table. We're going to learn more about the periodic table as time goes on, but that's the main things. Let's talk about the Bohr model of the atom. So Niels Bohr, he is the student of Ernest Rutherford, who did the gold foil experiment, and he discovered something else. He discovered that electrons are at specific energy levels around the nucleus. And so he made his model like this. You have your nucleus here. You have your first energy level right there, your second energy level, third energy level, and so on. Okay? You can have more than 3. I'm just drawing 3. Okay? So this is the nucleus. He knew about the nucleus because Ernest Rutherford discovered the nucleus. And this first energy level we call n equals 1. Second energy level, n equals 2. And this will also be on the test. N equals 3. So n is the principal quantum number that represents the energy level. Or we also call it the shell. So in this particular atom, what is the principal quantum number for the valence shell? What? On this particular atom, what is the principal quantum number for the valence shell? Do you remember what valence is? Yeah, it's number 3, the highest energy level. You with me? So I'll use that name, shell, as the energy level. So it's kind of like an onion where it has different shells, different layers, right? Okay? This is not how the atom really is today as we know it, but this is a good way to draw it. Okay? So what can n be? N can be equal to 1 all the way to 7 in this class. As we know it today, that's what they are. Where do you find 1 through 7 on the periodic table? The periods. The periods are energy levels, basically. There's some exceptions and some weird things going on. I'll show you that in a minute. Any questions about that? All right. Moving on. A lot of info today, huh? Let's get another periodic table out. And if you guys want a brand new periodic table to start with new notes, this will be a good time to make a new notes on a new periodic table. So if you want to, okay, we're going to talk about the electron configuration now. And I'm going to show you how to figure out the electron configuration by using the periodic table. Now this part is generally a hard topic for students to grasp. Once they grasp it, it's easy. So pay attention, ask a lot of questions as we go through this process, okay? So I'm going to show you how you figure out the electron configuration by looking at the periodic table. First, let's do a few things. So shells, that's the period. Or in other words, the energy level, right? And that is n equals 1 through 7. And then we have subshells. There are 4 subshells that we deal with in this class. The first 2 groups, including helium, are the first subshell, S. Whoops. Subshell S. The rest of the main group elements is called the P subshell. So I'll write that right here. There's my S. There's my P. And the transition metals, that's my D subshell. And these are all lowercase, by the way. And the last group are the intertransition metals. This is my F subshell. That's it. S, P, D, and F. So you guys ever make an alphabet that you and your club members can know when you was a kid? You can make up your own wording system. You guys ever do this as kids? Okay. Well, this is kind of what this is. It's just a code that we make to determine where the electrons are. All right. So let me tell you one more thing. Orbitals are where electrons live, or the homes of electrons. And each orbital holds a maximum of 2 electrons. Okay, so when we're talking about the electron configuration, I want you to not see all of the elements. This is the table of electrons. And how do we count? What number do we start with? 1, right? We start with number 1 every time we count. We're going to be counting electrons here, so we're just going to start with number 1. And then when we're done with number 1, we do 2, and so on. And we go in order. Same thing here. We got to go in order. And here's the order. 1, 2, 3, 4, 5, 6, 7, and so on. Good? I'm just telling you to go in order. That's all. I didn't show you how to do it yet. Okay. The s orbitals the s subshell has only one orbital. Can we make sense of that by looking at the periodic table? 1, 2. 2 electrons per orbital. Do you get that? So if we're counting, we got 1, 2. The next S subshell is 3, 4. And the next one's 11, 12. There's always just 2. You following? Using that pattern, how many orbitals does P subshell have? Every orbital has 2 electrons. S only has 1 orbital because there's only 2 electrons. 1, 2. Should we do the same thing for P?
How do you know?
1, 2.
So what are you counting? It's hard to see. Oh.
1, 2.
Oh.
1, 2. 1, 2. It would be 3. So the P has 3 orbitals. Does that make sense to everybody?
So each
For
column.
every, yeah.
Every 2 columns is one orbital.
Let me just show you another way to think about this. When we count, we have 1, 2, 3, 4, 5, 6 electrons in that p orbital, in the p subshell, right? 6 electrons, but you have to have 1 orbital for every 2. What's 6 divided by 2? 3. Good? What about D? D has 5 orbitals. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 divided by 2 is 5. Are we good? And what about F? Remember, that's not this one. These ones go up here. But look on your periodic table. There's 14 different columns in the F. 14 divided by 2 is 7. 1, 3, 5, 7. Are we good? Okay? You'll be asked a question like that on the test. All right, you ready for the electron configuration? I just gave you showed you how to use the periodic table, where the S, P, D, and F are, so that we can do the electron configuration. You ready? Okay, stop me anytime you have a question. Okay, so I'm going to give you the simplest, well, not the simple, one of the simplest, 1s2. This 1 represents the principal quantum number n, or the shell, or the energy level. In other words, the period, right? Not always the period. We'll get there. But that's the shell. The S we talked about as the subshell. And the 2, number of electrons in subshell. Are we okay with that?
So is the entire periodic table a shell, or is...
No. Nope. The periods are shells. Here's shell 1, shell 2, shell 3, 4, 5, 6, 6 and 7.
Oh, okay. And then what are the bottom two in F?
Okay, we'll get there.
Okay.
Any other questions? All right, let's do hydrogen. Hydrogen's electron configuration. What energy level or what shell or what period is hydrogen in? 1, so its shell is 1. What subshell is hydrogen in? S. Or I shouldn't say hydrogen, I should say the electron that hydrogen has. Well, it only has 1 electron, right? So we start with number 1. So it's going to be in position where hydrogen is, right? So it's 1s. How many electrons does hydrogen have? 1. Boom. That's the electron configuration for hydrogen. Now let's do helium. 1 S 2. Do we get that? Hydrogen has 2 electrons. They're both of those 2 electrons, the first and the second, are on that first energy level, first shell. So it's 1s, and we're going to count them. 1, 2. 1s2. Are we good? Okay, let's go to lithium. Be careful. Can there be 3 in an s orbital? Orbitals can only have 2. An s only has 1 orbital. What number do we start with when we start counting? 1. We always start with 1 when we count. The first 2 electrons are right here and right here. I'm not talking about hydrogen and helium. I'm just talking about the electrons. Yeah. Okay?
So wait, is it
So,
3?
well, lithium has 3 electrons total. The first 2 electrons are on that first energy level. And there's only S on the first energy level. How many electrons can fit in that S?
3.
Only 2. S can only fit 2. Then, if we look at our periodic table, lithium is on energy level what? 2. So now we put 2. And what subshell is this third electron in? It's still in the S group, guys. Still in the S. You with me?
And then is it just an S or is it a 1 after the S?
Well, it's an S first. And how many electrons are in the 2s? Just 1. Because we have a total of 3. There's 2 there, and there's 1 right there.
I don't understand. Can we do another example?
We sure can. Questions? We're just counting, one at a time.
So we are just doing that, how many electrons can fit in how many shells? That is like 2, 8, 8, 18, 18, 18 like that.
No, we're not doing that yet.
So the periods.
You got something stuck in your head. Let's get it out for a minute and let's do this. Good? And maybe this might help. I'll see. Let's draw a Bohr's model for hydrogen. That's what Bohr's model looks like, right? It has one energy level, one shell, where n equals 1. And it happens to be S because we see here it's in the S subshell. Has 1 electron. There it is. Helium still has 1 energy level, but it has 2 on that first energy level. We can't have more than 2 on that first energy level. Our periodic table shows that. On energy level 1, we can only have 2. On the first energy level of every element has 2. Can't have more than 2. And it's always S.
So lithium, because it's on the second period, we count both the helium and hydrogen.
No, we don't. We count electrons. We are only counting electrons here.
So we count the first 2 electrons.
Yeah, here's the first electron. On all elements, that's the first electron. Here's the second electron. This is the periodic table of electrons today, ladies and gentlemen. Here's the third electron. Here's the fourth electron, all the way down to the 118th electron. Are you with me? We're not talking about protons and neutrons. We're just talking about electrons today.
So can we do BE as an example?
We'll do a lot of them as an example. Let's draw the Bohr's model for lithium. On the first energy level, how many electrons fit on the first energy level? 2. And there they are. How many's on the second energy level? Only 1. Lithium only has 3. 2 on the first. You have 1 more. Good? So let's do beryllium. How many electrons does beryllium have?
5.
Count again. Beryllium, Be.
4.
4. Okay, so if we draw the Bohr's model, 2 on the first energy level. Can you fit more than 2 on the second energy level? Yes, because there's more room. Remember, electrons are negative, they repel each other, right? You can, when they're close together, you can only put 2. How many can fit on that second energy level? 8. Can you all see this, guys? 1, 2, 3, 4, 5, 6, 7, 8. Good? The rest of it gets weird after that. I wouldn't try to stick that in your head quite yet. So we're going to have 1, 2. 1s2, 2s2. But again, looking at the periodic table, here they are. 1s, 1, 2. 2s, 1, 2. We only counted 4. We're going to stop at 4.
So the first number represents how many rings out.
The first is the energy level, or the shell, or the period type. It's not always the period. We'll get there. The second one is the subshell type. And the number is how many electrons are in that subshell. Are we good? Okay, let's go to neon. If we draw the Bohr's model, how many are on the first energy level? 2. How many are on the second energy level for neon? Let's look at the periodic table. Oh, there's neon right there. How many? 1, 2, 3, 4, 5, 6, 7, 8. So on our Bohr's model, we have 8 electrons. And this is how we draw it. Is this how it really looks? No, it doesn't look like this. This is just how we draw it. And I'm not going to have you draw these. I'm just showing you. Okay? So what's the electron configuration for neon? 1s2, 2s. How many can S have? Only 2. How many electrons have we used so far? 4. How many do we have left? 6. If you look at neon, it has 10 total. We used 2 on the first energy level. Then we used 2 more on the second energy level. But we're only to here. We have 4. We're only to this one right here. Let me erase some of this stuff because I'm just... Okay. So we counted to 3 and to 4. Now what electron number are we on? What's after 4? 5. And here it is. There's 5, 6, 7, 8, 9, and 10. We have 6 more electrons. What energy level are they on?
3?
Look at it. Look at it. Here they are. What energy level is this? 2. We're still on energy level 2. So it's 2, but what subshell are these electrons on? P. And how many? 1, 2, 3, 4, 5, 6. Now, P has 3 orbitals. How many electrons fit in one orbital? 2 fit in one orbital. 2 times 3 is 6. So we call it 2p6. Are you following? Do some more? Okay, let's do which one? Carbon? Let's do carbon. Well, that was weird. Hook 'em. Okay, hold on. So we got carbon. How many electrons does carbon have? 6. Because its atomic number is 6, right? We're talking about neutral atoms. That's all. Okay. And how many are on that first energy level? 2. And what subshell are they a part of? S. Do you see the pattern here? The first two electrons are always going to be 1s2. For every element besides hydrogen, it's going to be 1s2. That first, they'll be the same. We use 2. We have 6 total. That means we have 4 more. Where can the next 2 electrons fit? 2s2. We used 4. We have 2 more. Where are they going to go? Right here and here, right? 2p2.
So the S's can only, it's like a box and you have 2 electrons in the box and only fit 2 electrons with the S's.
If you want to think about it that way. But 1, 2. 1, 2, 3, 4, 5, 6. What's D going to have? Up to what? Count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. What's F going to have? Count again.
5 orbitals.
14.
Yeah, 14.
Are we good? Should we do a heavier one? Let's do iron. One S. Uh-oh, are we still lost?
We're just looking for iron.
Iron, oh good. It was number 26, so we have 26 electrons. So we're going to start with what number? 1. So 1s, 2, then what? 2s2. So far that's 4. We got to go to 26. So what's next? 2p6. Right? So far that's what neon looks like. And that's only 10. We got to count to 26. We got a ways. What's after 2p?
3s2.
Oh, then we go down to 11, which is on energy level 3. Now it's back to the S. And how many can we fit in the S?
2.
Only 2 ever. And what's after that? We did 11 and 12. Then we got 13 to 18. 3, it's still energy level 3. P6. Then after, so far that's 18. Then we go to 19 and 20. What's that? 4s2. Now here is where it goes different, ladies and gentlemen. We got to watch. Pay attention here. It goes back down to 3. I'll tell you why in just a minute. 3D, count them. 1, 2, 3, 4, 5, 6 until we get to iron. 3d6. Now why does it go down to 3 again? So it goes back to your question. On energy level 1, you can put 2 electrons, right? Energy level 2, you can fit a maximum of 8 electrons. Why? Because there's more space, right? Do you think on energy level 3 you could put more than 8?
18.
Yeah, oh, it turns out you can put 18. Well, let's see. If we look at the periodic table, it looks like there's only 8. We need 10 more. Where are they coming from?
Level 4?
Right there. The 3D. Now here's why it does that. You don't have to know why it does that, but do you want to know why it does that? Okay, so we have the first 2. We can only put 2 here, because if we try to put another one there, it's too much repulsion going on, right? And they're fighting this saying, get out of here, right? So we can't put that third one on that first energy level. It can only have 2, maximum of 2. The next one has a maximum of 8. And then it starts saying, hey, get out of here. We can't have any more. So we get out more. And then we do 8 again. And if I try putting one right there, is there a little bit of repulsion going on? There is. So it takes a certain amount of energy for that electron to be right there. And it takes a certain amount of energy for that electron to be right there. It turns out it's less energy to be right here because there's no repulsion. In fact, the first 2 before it goes back to there. Now there's repulsion and extra energy to bump out, right? So then it starts filling them in down here. Up to 10 more. Now that's a simplified explanation of what's going on. Okay? But here's what you should know. S starts at shell 1. Right? And we can easily see that on the periodic table. Here it is. S starts at shell 1. Right? P starts at shell what? Let's see. Let's look at it. Oh, it's 2. You see that? P starts at shell 2. D starts at shell 3. Oh, this is nice. Any guesses what F starts at?
1.
4. It starts at 4. So that means, let's get another periodic table. That one's kind of messy. Sorry. Okay, so we got S starts at 1, P starts at 2, D starts at 3, and F starts at 4. Well, it's not that one. This one right there. It'll be the first one on your guys. It's number 58. We're good? So just know that. You still have to count in order. So after you get to 20, you got to go to 21. After you're at 57, where do you go? 58, which is in a different subshell. You still have to count in order. Are we good?
So everything goes by numerical value instead of visual.
You just got to count in order.
Yeah.
Okay. Are we good?
Do we have one more example of like a longer number?
Yeah. Let's do. Let's do xenon. I won't give you anything higher than xenon on the test. You guys figure it out.
What number is xenon?
Number 54. If you want to do it by yourself, keep going. I have the answer up here if you want to see what it is.
So it goes 3s2, then 2p6, or 3p6.
3s2, then 3p6. We don't go back to 2. We already did energy level 2 for P. Got to go in order. So if you look at this, for S, everybody watch up here for a second. For S, we got 1, 2, 3, 4, 5, 6, 7. For P, we got 2, 3, 4, 5, 6, 7. Same thing, it just starts at 2, right? For D, I used the wrong color, but sorry. D starts at 3, and then it goes 4, 5, 6. Still goes in order. And then F starts at 4 and then goes to 5. Still goes in order. So you just have to know 1 starts at 1, starts at 2, starts at 3, starts at 4.
Okay.
Are we good? And you still count in order. So here's the answer for xenon. We're almost there, guys, but we've got a little bit left. Do we have any questions on the electron configuration? Yeah.
How come when it gets to subshell D that it goes down the energy level again? Like, I just don't really...
It has to do with how much energy does it have. It takes so much energy to go to the next level. And it can't, remember we talked about, and actually I'm glad you asked this question because this is going to be on the test. Principal quantum number. What does quantum mean? Specific. So an electron can, if it goes right here and right here, it cannot go somewhere in between. Cannot. It has to be specific energy levels. Okay? And so if we're talking about this right here, well, electrons don't want to put forth effort or give off energy unless they have to. They're kind of like us. We're not going to do something unless we have to. Isn't that right? Isn't that kind of how we are? Naturally? Okay? So they're going to go the least energy as possible. So an electron can come here or it can go here, but it takes less energy to go there than it does to go there. It takes less energy to go there than it does to go there. That's why we got the 4s2 first. But then if it wants to go there, it takes less energy to go here, 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 and here, and all of the rest.
So, just always go down a level?
But just know this. S starts at energy level 1. P starts at energy level 2. D starts at energy level 3. F starts at energy level 4. 1, 2, 3, 4 in that order. And then when they go down to the next one, what's after 3? 4. What's after 4? 5. What's after 5? 6. Same with F. 4, then 5. The only thing you got to remember is where it starts. But the reason is, it's because it's a slightly less energy. to do that. Are we good? Any other questions? Are we getting it down for the most part? Okay, I'm going to give you a couple more things about the electron configuration. We might not be able to finish tonight, guys.
Next lesson is better.
That means don't take the test today or this weekend, right? Okay, here we go. Let's do sulfur. The electron configuration for sulfur is 1s2, 2s2, 2p4. You with me? I'm not memorizing these, guys. I just know where it is on the periodic table and I can see it. Are you with me? But there's a shortcut. You guys want to know the shortcut? You have to know the shortcut on the test. Here it is. What type of element do most elements want to be like?
Noble gas.
Noble gases. So we find the noble gas just before sulfur. Which noble gas do we have just before sulfur? That's just after sulfur. What noble gas is just before sulfur? Sorry. You're right. I says I knew this in my head. This is not sulfur. What is this? This is oxygen. I'm sorry. I messed up.
How can that be 16?
It's not. Here it is. 3s2, 3p. There it is. Oh, okay. My bad. Yes, you're right. Neon is the noble gas just before sulfur. Sorry about that. Are you good?
Is phosphorus not a noble gas? Or is it one
No,
of
it's
the-
not. The noble gases are in group 18.
Oh.
Good? Okay, so this right here is the electron configuration to what element? 1s2, 2s2, 2p6. That's neon. So for sulfur, the shortcut method, or the noble gas method, is to write the nearest, or the previous noble gas just before the element in brackets, not parentheses, but brackets, and then write whatever we have left over. Are we good? Should we do another one? Let's do iron. Iron is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6, right? What's the noble gas just before iron? And that's what it is right there. That's argon. What's left? 4s2, 3d6. This is also iron. A little bit nicer, yeah? Okay, ladies and gentlemen, I got to show you. Do not take the test this weekend. We're out of time. And we're so close.
You mean the unit test, right? When you
The unit test one. Don't take it yet. Is that going to mess you guys up?
I could use more time to study.
Or would you want to finish it tonight?
No.
Okay,
I think it's too rushed.
good call, good call.
Give us something to chew on over the weekend, and then we come back fresh Monday, or Tuesday.
Sounds good. And hopefully we'll get caught up Unit 2 is the unit that a lot of the students slow down and then they hurt themselves, grade-wise. So let's make sure we get Unit 1 down. Make sure we still remember it and study it as we go. You still have to know it. Okay? Bless you.